There is a very simple relationship between the speed of light, the frequency of light, and the wavelength of light. And the truth of the matter is you already know it. You already explored it when you studied waves in the last semester of physics, and you probably remember that the speed, velocity of a wave is equal to its frequency times its wavelength. Does that look familiar? I hope so. And so when we're talking about electromagnetic radiation or light, then really V just becomes c, the speed of light, right? And that has the same relationship as before. All right? So we can always get the frequency from the speed of light and from the wavelength, or the wavelength from the speed of light and the frequency. It's very, very simple. So let's just do an example with respect to a bee, okay? When a bee sees that flower bullseye in ultraviolet, she sees a wavelength of about 10 nanometers reflected from the flower into her eye. What is the frequency of the light that the bee sees, right? Now, quite simply, we know that C is equal to 3 times 10 to the 8 meters per second. Very simple, right? So if I want to know what that frequency is, then frequency from this formula is simply C over the wavelength, right? Which is 3 times 10 to the 8 meters per second divided by 10 nanometers, which is 10 times 10 to the minus 9 meters, right? So my frequency then is going to be 3 times 10 to the 17 hertz. Now, a hertz is really just a cycle per second, or you can think of it as 1 jiggle per second. But frequency really just means how many times does that light oscillate in 1 second, and that's 3 times 10 to the 17. That's a preposterously huge number, and hopefully it just gives you some sense of the magnitude and scale of how fast electromagnetic light actually vibrates. Okay, so that's that. Pretty basic. And I think it's worth sharing. I said a little bit before that we found out that the speed of light and electromagnetic radiation were connected, and that's how we kind of knew what light was actually made of. And so it turns out that this number of 3 times 10 to the 8 meters per second, it really comes from 1 over the square root of the electric permittivity and the magnetic permittivity. That's it. How cool is that? So these two little friends that have been kind of, hovering around in the background through this entire course, put them together, take the square root, and you actually get the speed of light. And so when people saw this, they're like, oh, that cannot be a coincidence. This must mean that light is actually made of these propagating electric and magnetic fields. Okay. We're going to do a couple misconception questions. Number 1, it says, which of the following travel at the same speed as light? We have radio waves, microwaves, radar, which are basically radio waves that you bounce off things so that you can see if something's there. Ultrasonic waves, those are like for an ultrasound. Infrared radiation, cell phone signals, gamma rays, X-rays. Which one of those travel at the speed of light? You know it's a trick question because they all travel at the speed of light. Can't trick you. All right. Another misconception question. If an electron in a wire is vibrating up and down 1,000 times per second, they will create an electromagnetic wave having a wavelength of 100 or 1,000 meters? No, not a wavelength. It's telling you how many times per second it's jiggling. A frequency of 1,000 hertz? Yes, obviously, right? How many times you vibrate per second is the frequency. So the answer to that would be B. C, a speed of 1,000 meters per second. We're not talking about a speed. By the way, if it's an electromagnetic wave, the speed would actually be 3 times 10 to the 8, which you know. And we're not talking about amplitude either. Let's talk about a fun factoid, okay? This image shown here was taken by the Hubble telescope. This was one of the first telescopes that was actually placed outside of our atmosphere so that, the atmosphere acts kind of like a lens, and it diffracts and refracts and blurs light, right? But you can get a much more potent picture of the universe if you actually put your telescope outside the atmosphere in orbit. So the image here shown It's from the Hubble telescope, and these are not stars. How cool is that? Not stars, but actual other galaxies, hundreds of millions of light years away. This means that we are not just seeing these galaxies as they appear today, but as they appeared hundreds of millions of years ago. When we take a picture of space, it's almost like a time machine. Because if something's, 100,000 or a million light years away, that means it took that light a million years to get in your eye. So it's a million-year-old light that you're seeing, and you're seeing what these galaxies looked like in their state a million years ago. Some of these galaxies may no longer exist. Some of them may have crashed together and merged, but we're getting this snapshot of ancient history. Okay? It is possible that someone living on a planet near one of these stars, inside one of these galaxies, would look at the Earth through one of their own telescopes and they would see dinosaurs. They could be doing this right now at this precise minute and be seeing dinosaurs because just now the light from the time of dinosaurs would be reaching their telescopes. All right? Fun food for thought. All right. That's enough for this little miscellaneous video. In the next video, we're going to be discussing the concept of polarization.